Okay, now we move on to Gauss's law. Before I go into Gauss's law, I just want to remind you what the electric field represents. So electric field E at a point is merely the force a unit charge would feel if it were at that location, i.e. the force per unit charge. Gauss's law provides an alternative formulation of the relationship between electric charge and electric field. It is logically equivalent to Coulomb's law, but in some situations it is far more convenient to use. The content of Gauss's law is suggested by consideration of field lines. Let's define flux as the number of field lines that cross a given area. Let's give it a symbol gamma, and we're going to call that flux. Remember, in the very last section we talked about the flux using the vector field A. Now we're going to begin to talk about using the flux with the electric field vector E, the force per unit charge. This E perpendicular sign here is the component of E perpendicular to the surface. If we add up all the perpendicular components of E for every point on the surface, this will then be the total flux through that surface. Let dA be an infinitely small section that we can sum up across the whole area like so. So we can let dA reduce to this very, very small section, and then of course we form the integral, so we can find all of these perpendicular components of E all over this surface by forming the integral and integrating over this whole surface. So that's what that equation represents. So E cos theta is the perpendicular component of E across the whole surface. And then of course, as we know in the previous discussion on flux through surfaces, we know that E cosine theta is the same as E dot dA. So we can just shorten this and write this as the integral of E dot dA. Now let's imagine a point charge with a sphere around it as small as the charge itself. Then it's obvious that the flux moving outward is proportional to the charge enclosed, and this is what Gauss defined by writing that the flux is equal to the surface integral of all the field lines leaving the surface is simply equal to the charge enclosed. So this here is Gauss's law, where 1 over E hat is the proportionality constant. So this is known as the permittivity of free space. It's the electric permittivity, okay? And this is the proportionality which defines Gauss's law. So to summarize, this equation here states that the total electric flux out of a closed surface is proportional to the total charge enclosed. If charge is outside the closed surface that we are evaluating, then this equation here would equate to 0, since flux lines that enter on one side will exit on the other side, on the opposite side. So if the charge is not inside the sphere, it's out here, then obviously the flux that enters this side of the sphere is going to leave the other side. So then if we calculated the flux upon that, using Gauss's law upon that whole sphere, we'll have that this equals 0. When we're going over the whole surface, we'll write the circle like this. This symbol here will represent the surface integral over a closed surface. Now the interesting thing, of course, if the field is uniform and perpendicular to the area, then this here can be written as like so. Because obviously then we've got a uniform field which is completely parallel to the unit vector of the surface area. So then all we have to do is just whatever the vector field E is just multiply it by the area. But that's only in the condition when the field is uniform and perpendicular to the area that it's going through.